Okay, I guess we'll get started. Welcome to the March 2021 edition of Green Infrastructure, Climate and Cities. This is a monthly seminar focusing on the unique challenges that climate change pose for cities and what we can do about it. My name is Franco Montalto, and I'm a professor here at Drexel University in the College of Engineering and one of the lead principal investigators on the Consortium for Climate Risks in the Urban Northeast, a NOAA-funded team of researchers and universities investigating on climate change impacts in our region. We are pleased to promote this event as the third CC-run seminar to be held during Drexel's Climate Year, a period during which we here are celebrating, supporting, and cataloging our climate action. This evening's event focuses on data and tools in adaptation planning. Let me advance. Okay, so for those of you joining us for the first time, CC-run began hosting a series in 2014. All of our seminars are live cast, archived, and accessible on the CC-run website. Please go to ccrun.org to view any of our previous seminars there. We offer continuing education credits for attendees of today's session. You can email us and we will document your registration and participation in the event. Another note, please use the Q&A box to submit your questions. You can also upvote other questions and raise your hand. But please just reserve the chat for technical questions if you're having trouble with any of the seminar of the webinar features. As a small act of respect and honor, we've decided to include a reminder at the beginning of each of these events that the Northeast US that we focus on is the historical homeland of the Lenape. And quoting the Lenape Center, due to centuries of colonialism perpetuated by genocide, forced displacement, and systemic oppression, today, the Lenape diaspora is dispersed throughout the US and Canada. So our hope is that we may learn how to care for our small corner of the world with the same respect and care demonstrated by Indigenous peoples here and elsewhere around the world. So as I said, tonight's session will be focusing on tools for adaptation and climate change. And we have three speakers who will tell us about three map-based decision support tools. Those three tools are the Hudson River Flood Impact Decision Support System, AdaptMap, and Vision Maker. And I won't give you any more details there. I'll let the speakers introduce those tools in their talks, but I'll tell you a little bit about our three speakers. So Kytt MacManus is a GIS development analyst at the Columbia University Earth Institute Center for International Earth Science Information Networks. He's also an adjunct lecturer in Geographic Information Systems at Columbia and in the Sustainable Development Program of Ecology, Evolution, and Environmental Biology at Columbia. Kytt has extensive experience with global data sets and web applications for a variety of different applications, which he'll talk about today. Our next speaker is Dr. Philip Orton, who's a research associate professor of ocean engineering at Stevens Institute of Technology in Hoboken, New Jersey. Stevens is one of the core members of CC-run. Phil earned his PhD in physical oceanography from Columbia and has published in over 40 peer-reviewed articles on physical oceanography, storm surges, flood risk assessment, air-sea interactions, coastal meteorology, and other topics. He's also a member of the New York City Panel on Climate Change and was appointed by New Jersey's governor to serve on the New Jersey Wetlands Mitigation Council and is also a contributing author to the IPCC 6th Assessment Report. Finally, we have Eric Sanderson, who's a senior conservation ecologist at the Wildlife Conservation Society, where he writes about the past, present, and future of nature in New York City. He's the author of Mannahatta, A Natural History of New York City, and Terra Nova, The New World After Oil, Cars, and Suburbs. And he was lead editor of Prospects for Resilience, Insights from New York City's. So with that introduction, I will stop sharing and hand over the presentation to, I believe, Kytt.
Kytt, before you start, I'm going to just share the results from our poll earlier, like from a minute ago. So it looks like we have a good chunk of people from government. About 40% of our audience work in the government sector. We also have a decent distribution of for-profit, nonprofit, and academic. Thank you all for joining us. And if you wouldn't mind typing in the chat where you're joining us today, it'd be great to see how many folks we have from the Philly region, New York City region, or from elsewhere, just so we can kind of have a sense of where everyone's coming from. Go ahead, Kytt. Thank you.
Sure. Thanks, Franco, and thanks, Corinne. As Franco mentioned, my name is Kytt MacManus. I work at a research center at Columbia University called the Center for International Earth Science Information Network. We never ever call it that, though. We usually just call ourselves CEASON. So take the acronym in, ingest it, and then forget about it. We're CEASON. Advance to the next slide. So, CEASON is a group that works at the intersection of natural, social, and information sciences. So it's an interesting place to be in. We're actually one of the first groups to provide geographic data for download on the internet back in 1995. And since then, the work has taken our group in a number of directions. Next slide. So this is just an example of some of the projects that we've been spending time on over the past decade or decades. Probably, the most of my efforts are on the first line in this list, which is the NASA Socioeconomic Data and Applications Center. But we also do work that is, not federally funded, including some of the local research I'm going to talk about to you today, and research from the Bill and Melinda Gates Foundation is one of the primary sources of our work these days, looking at population mapping and human environment interactions. So go ahead to the next slide, and Eric, you can introduce WCS.
Yeah, hi everybody. I'm Eric Sanderson from the Wildlife Conservation Society, or WCS. We run the Bronx Zoo and the New York Aquarium and the other zoos in New York City, and then also have a large global field program that works on wildlife conservation around the world, which is the part I'm associated with. But we also do a lot of work around New York City, and that's what we're going to be talking about today. Cities are, essential to conservation of wildlife everywhere because people mostly live in cities. And that means to connect our urban people to nature, we need to help them appreciate what they can do to make a difference. And Vision Maker is that tool that allows people to create and share their ideas of what they'd like to see for the future of the city. So I'll look forward to telling you all about that soon.
Thanks, Eric. And I'm Philip Orton, and I work at Stevens Institute of Technology in Hoboken, New Jersey. There's a school with about half and half graduate and undergraduate students, 6,000 total, focused on engineering science, and also a little bit of an unusual flavor of finance, given the proximity to Manhattan and subway ride over to Wall Street in Midtown. And specifically, the people I work with mainly are at Davidson Laboratory, sort of a historic hydrodynamics laboratory with about 10 research faculty focusing on naval architecture, coastal ocean engineering, physics of the ocean, and marine hydrodynamics and maritime systems. All right, so today's seminar goals, I guess I'm taking myself off, putting myself up on video now. The seminar goals are part one for the first hour or so, maybe a little over an hour. We'll learn about recent innovations in online climate hazard and adaptation data tools. And then we'll take a brief tour of 3 examples of these map-based tools within that hour. And then part two, for people who want to stick around and see demos of the different GIS mapping applications, these tools that we're talking about in part one, they can stick around for longer and learn more details about them and how to use them and access them. All right, go ahead, Kytt.
Sure. So as I know I'm preaching to the choir here, but it's worth quoting the IPCC in 2014 when they said that climate change threatens people around the world, but particularly in locations where concentrations of people can be expected to overlap with concentrations of physical hazards resulting from climate change. So, this is the backdrop that informs why we're doing this work and why we're creating these interactive tools to help inform future decisions. At the one end of the spectrum, more and more these days, we're hearing people talk about managed retreat and, trying to understand at what point do we need to take adaptation to the next level and start moving masses of people away from coastlines where there happens to be high concentrations of people and high concentrations of physical hazards. Next slide. So, the reason why we think it's important to communicate this information in a map-based system is because the science, as we all know, it can be pretty complex. When we map the data, though, we appeal to something that's innate in humanity, and that's human sense of place. So place is this idea that, it's not just a nebulous location. It's a portion of space that's designated for or being used by someone. In other words, it has some cultural meaning, something that people relate to, and that they can create their mental models based on understanding the places where they've been and the places where they might want to go. So these decision support tools, they're important because they enable local decision makers to take into account their community's history and their values and their sense of place, and to look at possible future scenarios and then make decisions that are in accordance with their own values and risk tolerance. We understand that different communities are going to approach these issues differently. So the decision support systems, they, more than anything else, they allow for that variation in viewpoints and, for people to interact with the scientific information, to understand it in a place-based type of way, and then to choose what to do, not just in a back of the envelope, everyone doing the same thing type of way, but, in a way that makes sense for their communities. So Philip, you can pick up.
Yeah, okay. So the first couple tools that we'll be speaking of have to do with mapping flooding and adaptation to flooding, or flood hazards and then adaptation to flooding in that order. And I'll review these in more detail in a moment. And then the third one is more broadly about climate adaptation. And so first, I'm just going to introduce these different tools in a broader sense. So, and just thinking initially about flood adaptation and flood risk, some examples of really useful tools that are already out there that we have to think about when we're trying to innovate upon them and do our own, online tools. One of them is Surging Seas, and then the second one is from NOAA, and I'll show more briefly. Surging Seas is really useful. As an academic, I still go to it because I know exactly what it does. It takes water levels from normal high tide, and then you can add different increments of sea level rise on top of it, and then it spreads it over in a sort of bathtub flood mapping procedure. And that can be really useful to look at sometimes. So, and also it quantifies the population and a lot of other metrics within those areas. So it's really useful. It's applied nationwide, if not worldwide. They definitely have tools also that are worldwide. So really useful tool that I often use. Another one, as I mentioned, was NOAA's Sea Level Rise Viewer. These mappers tend to be static mapping, as I mentioned, bathtub mapping. So this is from New York City Panel on Climate Change 2015 chapter that I authored, where we compared the dynamic and the static approach to mapping. The static mapping uses this extrapolation approach called bathtubing. If you look at sea level rise, it simply superimposes the sea level rise on top of the high tide or on top of the extreme event 100-year flood, and assumes that there's no interaction or no more complex physics, and they superimpose. And I'll address what the accuracy of that a little bit in today, but we'll mainly be focusing on the web tools. And then adaptation can't really be tested very well unless there's just a wall or something raised with that type of static flood mapping. But with dynamic coastal flood modeling, or also known as hydrodynamic, meaning water dynamics or water movement and forces, with that type of modeling, which is what we used in the first two mappers we'll show today, it's a physics-based computer simulation that includes all the different forces on the water. It gives a time-dependent solution. For some of these mappers, there's a play button where you can see an animation of the flooding on a map instead of just seeing the peak water level, you know, the peak extent of the flooding. You can also put in, you have more sophistication with the ability to represent adaptations such as green infrastructure or gray infrastructure, and how green infrastructure might frictionally slow the water's movement and reduce the flooding. So that's the big benefits of the dynamic approach. Just a summary of some thoughts on data accuracy and the interactivity for web tools. One problem is that these mappers, you know, for certain applications, they're overly simplistic with this static flood mapping approach that's commonly used. And the solution to that, as I mentioned, is dynamic flood modeling. It can, if you have, you know, in most cases, it can provide more accurate data. You know, with GIS mapping, if you have really high resolution and more detail, actually, sometimes you'll capture a wall or something that's not resolved in a dynamic model. So there has to be attention paid to resolving levees and walls and things, but it generally can be more accurate type of flood modeling and mapping. Another problem is that people don't sufficiently understand climate and flood risks, nor the benefits of adaptation. And we really see that especially. And the solution to that can be that dynamic modeling can enable interactive quantification or interaction with a web tool, such that people could create adaptations and then learn from how they, you know, if there's rapid flood models built into them, as is one of our goals going forward, then they can see the impact on the water movement. And then the last problem is that, and this is sort of addressed with Eric's presentation today, a lot of these assessments, including my own, are more one-dimensional, focused just on monetary damage reduction, such as, you know, and that's often a complaint with the federal government's approach with the Corps of Engineers. They're a little bit more too one-dimensional. And so the solution, and this is actually happening within the Corps of Engineers too, there's a shift gradually, at least with them, toward looking at many different metrics of benefits. And we'll come back to that in Eric's presentation, where he's created Vision Maker, which has many different metrics that you can look at. So the three different interactive web tools are the Hudson River Flood Impacts Decision Support System. We'll spend about 20 minutes on that. AdaptMap, Flood Sea Level Rise, and Adaptation Benefit Mapper, my own typo there. And we'll talk about that maybe 15 minutes, and then Vision Maker for the final 15 minutes or so, which is considered an ecological democracy tool. AdaptMap is based on a part of New York City, Jamaica Bay, where JFK Airport is. But it's sort of, I'll also speak to the general potential for a flood adaptation mapper. And there is this progression within these three. The first one is just a hazard, more of a hazard mapper. It doesn't have dynamic modeling of adaptations, although there is information on it on the Hudson River system that shows information on adaptation. But then in the AdaptMap, the whole goal was to actually have adaptation demonstrations and how the adaptation reduces flooding. And then in the Vision Maker case, as I mentioned, it's more of a broad climate adaptation explorer that people have a lot of interaction with. They can design landscapes, design ecosystems. And in that one, it's got these multiple metrics of benefits. All right, so speaking about this first project, it's the Hudson River Flood Impacts Decision Support System funded by Nyserda. The big goal here was to first model in detail the flood hazards and their probabilities, and coming from combined tides, not mentioned here, tides, sea level rise, storm surge, and rain, which could come directly on water or through river stream flows. And there's a collaboration between CSUN and Stevens. This is a map view of the Hudson and its coastal estuarine areas, showing just a result from a 2012 paper that I published, where we found that if you ignore the freshwater inputs to a coastal flood model, which is what FEMA does for their coastal flood studies, then, and you also use a two-dimensional model that doesn't include any vertical complexity, such as the layering of saltwater and freshwater that occurs in an estuary, then you underestimate your flood, your peak water level by up to about 50% within this map area. So as you go up the Hudson, as you go up an estuary, you have increasingly large errors. And so we illustrated that well, and the federal government has actually really done a lot of work in the past 8 years toward a national water model and coupling national water models, meaning hydrology, with the coastal models and coastal forecasts, but it's still a work in progress. So, and this study was sort of an early innovation in looking at flood risk, where you combine these different sources of water instead of treating them as complete separate topics, the river flooding and the coastal flooding. These are two bar charts showing peak water levels on the left at New York City at the Battery, including Hurricane Sandy for 2012. These aren't really a time series, they're in temporal order, but they're just the top 20 events in both cases, back to about the 1930s. So that shows on the top left that it's extratropical cyclones out along the coast and tropical cyclones. On the right is Albany, so at the very northern part of the Hudson River, much more on the riverine end member of the topic. And there's a mixture of inland extratropical cyclones that bring a lot of rainfall and sometimes rain on top of snow, and the same tropical cyclones causing the peak water levels, peak top 20 over the past 80 years at Albany. So we're accounting for these different kinds of storms. We simulate many of them. So when it comes to the extratropical cyclones, they're not as unpredictable, and there's not really the same chance of extreme events that haven't been seen before. So we simulate just historical events and with their probabilities based on the frequency they occurred. But with the tropical cyclones, it's a common measure. There's been a lot of work by Carrie Emanuel and Ning Lin at Princeton, for example, and others that create synthetic tropical cyclone models, including an influence by insurance industry studies. So this is just showing a black line in the time series, top right. Let me use a special fancy pointer. Top right, the black line as we go through the, and sorry if it makes you dizzy, it's the tides, and it's a very rapid animation. You can see the coastal tides rising and falling. But the black line is at New York City, but the green line is up the river. So the Hudson River has a flood that's very much river dominated and more longer duration that comes after the storm surge. So the wind really causes the earlier storm surge, and then about 12 hours later in this case, and this is a synthetic storm again, kind of like Sandy meets Irene, if anything. The river flood comes later because of the whole watershed process and the confluence of those waters. So we account for synthetic tropical cyclones to try to capture any storm that could ever happen. If we want to look and try to quantify really low probability events, such as 1,000-year return period storms, then you can't just rely on 100 years of good historical data. You need to include these synthetic storms, in addition to the historical storms. So then this all gets merged, and this summarizes a lot of work in a very, very short, but you start with those historical data on the far left. You've got your synthetic and your real storms, your storm climatology, the storms with the different probabilities representing what you hope is all the types of storms that could hit. You get your flood modeling, and those flood modeling peak water levels. And then finally, the last step is to estimate on the x-axis, your return period, or the inverse of probability, versus your water levels. And a green line shown there is for extratropical cyclones for New York City, and a red line for tropical cyclones. And merging those probabilities together, you get the black line and the gray shaded area of uncertainty. And one big concern with this was to validate these models throughout, because there were big disagreements between FEMA and some other studies in the New York City region. So a lot of effort went in, even at the end, validating just an observation-based assessment and seeing if the model-based assessment, this is all model-based, what I'm talking about here, as informed by the observation. See if the model-based assessment agreed with the observation-based assessment, although that has a lot more uncertainty with such a limited period of several decades to estimate these low probability events. And one other thing I'll mention here is that we also then added on, that's mostly a 2016 Journal of Geophysical Research paper, but there's also a Natural Hazards 2018 paper that's looking at the Hudson River and merging these different types of wet storms and dry storms, and looking at the sea level rise problem. So I'll briefly show results from that Natural Hazards paper, and then I'll speak to the effect of sea level rise and how it's not a linear superposition problem in a tidal river like the Hudson. So top left is Albany, the very northern part of the system, It's dominated by the wet extratropical cyclones, the blue dashed line. So the black line merges the probabilities of the 3 different colored lines, but it's basically almost identical to the blue dashed line. That's those wet extratropical cyclones, rain on snow, big rain events. Tropical cyclones don't matter too much for the flooding at Albany, it turns out. And then the bottom right shows, well, bottom left shows the battery, the very southern ocean end member of the system. There, it's really a combination of extratropical cyclones drive the flooding for shorter return periods, the more frequent events. They happen many times every year, guaranteed. The tropical cyclones are much more rare, and they drive the extreme event sort of flooding. And that's why Sandy was such a big surprise. You go back a few slides here, and Sandy was just this one big surprise event that happened, hadn't been seen a water level even within 2 meters of that, about 2 meters less. In the past 180 years, there were some newspaper reports of events going back to the 17 and 1800s. So, you know, you could see it being a 100-year return period or something. These Sandy type events are very rare, but it's the tropical cyclones always that cause these much higher flood levels. And so you merge those probabilities together and you get your water levels at the different return periods. And then you go anywhere in the middle, like Poughkeepsie, halfway up the Hudson, you get a mixture of the different storm types leading to your final probabilistic information about flooding. So we get these different return period events and then we map them in the mapper. We also add sea level rise. We actually put a higher sea level into the simulations. So we learn dynamically how the water would behave. At some places, it's fairly simple. It's just superposition. The black lines are just linear superposition. The x-axis is water level without sea level rise. The y-axis is water level with sea level rise. So, you know, to think of superposition model, that's just to add water on and you get the line moves up in this plot. And the dots are the model results for many storms. You know, we're running thousands of different events for this type of assessment. Pretty computationally expensive, but the dots are all falling on that superposition line. So superposition is a pretty good predictor of coastal water level when you have sea level rise, just adding on that extra sea level rise to the flood level without sea level rise. But then when you look up a tidal river, I won't get into the details of the physics, but it's in the paper. Your lines you basically have less flooding than the superposition of the flood height without sea level rise plus the sea level rise. The end result's actually significantly lower, so it's somewhere between. It does raise the flood higher when you have sea level rise, but it doesn't raise it higher by the amount of sea level rise at the ocean end. So we capture this, and that's one of the benefits of using the dynamic models. So now I'll hand it back off to Kytt to talk about the mapper.
Thanks, Philip. Can you stop your share?
Yeah, sorry, you got to remind me of that.
No worries.
Go ahead.
Cool. Okay, so yeah, Philip, I think you did a great job of explaining the science behind what goes into this. And, now what I'm going to try to do is explain how we take that science and we turn it into something that's actionable in the communities for decision makers. So the Hudson River Flood Impacts Decision Support System, another long acronym, or HRFIDS, it focuses on 10 counties bordering the Hudson River. So importantly, the mapper does not include New York City, but it includes those counties north of New York City, all the way up to the Troy Dam north of Albany. Our target user group for this was municipal type planners. Many of you probably know that New York is a home rule state. So, every municipality has a planning board and a zoning board, and they need to make decisions based on good science. Many of the people they're appointed or they're on short-term memberships, and, they come from all different sorts of backgrounds. So the purpose of this tool was to create something that could be used by many different types of folks and to embed all of the great scientific work Philip described into that. So some of the key functionalities of the mapping application, the most important thing is to visualize different scenarios of flooding. So we have an array of different sea level rise and storm return periods that people can cycle through in the mapper. We also aimed to make the underlying data available for download. So there's an understanding that, you know, the impacts that we summarized and the flood models we created, they're not only going to be used for one purpose. So you never know what a user is going to do with the data set. So something that was important in this mapper is to make every one of those different scenarios available for offline use for people to use in any unexpected ways that they could imagine. We wanted to allow people to print their scenario maps, to be able to put them into applications to the DEC for permits, you know, some of which require that the towns take into account future sea levels. We also wanted people to upload and visualize their own data. Again, recognizing that these research projects, they're term limited. You know, so once our research ends, that doesn't mean that a municipality stops building new sewage treatment plants. So, you know, down the road, we wanted this to still be usable for folks to take their own shape file of new features and to visualize it on the map. And of course, all of this is produced in an interoperable way using open geospatial standards. So this is a view of the mapper itself. You know, as you can see, there's more than 90 different sea level and storm return scenarios to choose from. Within that, there's also many layers that could be visualized, you know, more than 30 different layers of different critical infrastructure. Each one of the scenarios has a corresponding impact summary. And as I mentioned, that the underlying data is available for download. The impact summary itself, what it consists of is descriptive statistics of potential impacts for the scenario. So this includes the number of potentially damaged buildings and the monetary cost of that building and contents loss, as well as, you know, some overlay analysis of the different critical infrastructure features that would be impacted by a given scenario. And, you know, as I mentioned, this data then can be taken offline in Excel and used for any number of purposes. So it's another look with the link. I will paste that link a little bit later into the chat for everyone. So you know, the mapper for each of these different 90 scenarios, it includes animations like those that Philip demonstrated. So part of what we wanted to educate this user group about was the fact that flood events, they're not occurring at one slice in time, they're actually occurring over time. And, you know, as we saw in Hurricane Sandy in Hoboken, you know, Hoboken filled up with water and then it took many days to drain back out. So we had in mind those users who may not be aware of such issues. The data itself, you know, it's flood models that is overlaid with 1 meter resolution local LiDAR elevation data. So very high resolution, but it is in fact a bathtub type model where, you know, the flood estimates are pushed over the land, looking only at the land elevations. You know, as we progress into the other tools, we can see more dynamic approaches. It includes potential inundation both with storm surge and without storm surge. So I won't list off these increments, but they're on the screen there for you to see. As you can see, there's a number of different storm intensities and a wide array of different sea level rises. We didn't attempt to say what date any of these would happen on. Instead, what we tried to do is build an envelope of possibilities that people could then themselves interact with and, you know, understand worst case and best case scenarios. They are all based on three-dimensional hydrodynamic simulations, as Philip was describing. So how do we come up with the different human impacts? we utilized a methodology similar to what's used by FEMA in their HAZUS MH flood model. So we adapted the FEMA HAZUS model to be run for many different scenarios, but we used similar depth damage functions and similar underlying input data. So this allowed us to estimate damage to buildings and their contents, as well as, coarser information as just the number of buildings affected and the number of different critical infrastructure facilities impacted. So there are quite a lot of critical infrastructure facilities. Many of these data sets, when we came to the table back in 2014 or 2015, they were siloed in different organizations. There wasn't one interactive database at the time of critical infrastructure. So a good part of our work was to integrate these data and to create that, common repository post-GIS database that had all of the critical infrastructure in the region. Here's a look at what it looks like. That the themes that we focused on were transportation, health facilities, schools, energy infrastructure, water treatment plants, emergency operations centers, and other miscellaneous assets. So we're looking here near Albany, and you just see some examples of the different types of emergency service centers in the area. This is showing a no sea level rise scenario with a 500-year return event. Another look at health facilities, institutions such as schools, libraries, and places of worship. The transportation infrastructure, including the bridges and the culverts, which are of particular importance, especially for those precipitation driven events. You want to make sure that the culverts are right sized. So look at some of the utilities in the area for power plants, as well as where there are personal water wells or water withdrawal locations. As we've seen in disaster events over time, sometimes there's a domino effect where a flood could then lead to contaminated water, which then leads to even bigger problems over longer time periods. So a bunch of different critical infrastructure data sets to look at and to see what types of scenarios might impact them. Another major component of the project was a social vulnerability index. So, at the block group level at Season, we created this social vulnerability index that is specifically focused on resilience to flood events. It draws heavily on the work of Susan Cutter from UNC, and is focused particularly, as I said, on resilience to those flood events. So it's just a theoretical framework that looks at dimensions of vulnerability. There's a lot of different demographic variables that could have an impact on someone's vulnerability and resilience. But, I won't get into the details of what a principal components analysis is exactly, except to say that we were able to reduce more than 30 different demographic variables into 5 major loading components. So in the principal components is a statistical analysis where you look at the variability of data. So somehow renting, not having a vehicle, being in poverty, and seeking out employment and services are statistically related. Therefore, they load into a single component. So we could label those components as deprivation, isolation, housing and age, ethnicity and occupation, and dependency. So necessarily there are some decisions to make when you do something like this about what variables are most important. But the principal component analysis allows you to deal with things like multicollinearity, or when multiple variables are expressing similar information. So how do you interpret something like this? So social vulnerability is a multi-dimensional measure. And again, we did it at the block group levels and also aggregated it for municipalities. When you look at this information, you need to look at the convergence of flood impacts in those areas that are socially vulnerable. And for a decision maker, you could then decide that those populations are the highest priority for resources during or after a major event. Again, ultimately it falls on the local decision maker, but the vulnerability index identifies those pockets within a community where, resilience may be less than in some other places. A third component that we looked at was natural resilience features. So there are some features of the landscape that can reduce the impacts of flooding, and we wanted to take those into account. So areas like wetlands and forests and existing floodplains, they're vital areas for handling riverine flooding. So what we've done is we've taken data from the National Heritage Program and from the DEC, and again, we've integrated them along with the critical infrastructure layers and the socioeconomic layers so that we can analyze the patterns in a given community of, maybe there's an opportunity for wetland migration in a community. We want to know that so that we can, people at the DEC and elsewhere who are working on this can prioritize their decision making as well across the region. So the impact estimates in our model, they are derived ultimately from building footprints. This was something that in 2015, it was impossible. From county to county in New York State, the amount of building footprints that were available or freely available differed greatly. So we took on additional project through Nyserda to create an open source building footprints database for first the Hudson River, but now for all of New York State. And that project is still in progress, but we utilized data from it so that we could assess damages at the building level using things like assessment data and then to aggregate them up into blocks and municipalities. So how do we interpret these impact estimates? They're in some way inexact. These assumptions we're making about depth damage functions based on FEMA, they rely on an understanding of the first floor elevation of a building, but the information on whether a building has a certain first floor elevation or not is not something that's readily available, even in these data rich locations. So there are assumptions that are made that, if a building was constructed after 1970, then it has met code requirements to have a certain first floor elevation. Is the ground truth actually that the elevation is that exact amount? We don't know. So that's why we say when you look at the impact estimates, the magnitude of the estimate and comparing it across scenarios is more important than the exact value, because that will actually be a good approximation of the impacts. So, that just to summarize, in the Hudson River tool, we focused on 10 counties north of New York City, extending up to the Troy Dam north of Albany. It utilized a simplistic model, which was a bathtub type flooding over land elevations, and he provided a bunch of descriptive statistics for planners and others to download and use in their own work. The next project I want to talk about takes that to the next level. The quantifying the value in communicating the protective services of nature-based flood adaptations project was funded by the NOAA COCA program. And when we talk about AdaptMap was born out of this work. So, you know, in addition to doing what we've done for the Hudson River in this AdaptMap work, we also looked at dynamic flood models and potential adaptations for future scenarios. So, Philip, do you want to chime in?
Take over. Yeah, this is a really fun project. I often say that it's my favorite project we ever had. And I think there's lots of interesting components to it. So this is just an overview. One thing we did, which really exciting, which Eric and I dreamed up, mimicking his Wilikia and his Mena how to work. We created an ocean model or an estuary water model of the historic systems, 1609, the 1870s, and then the modern day. So we have an estuary model that's pretty detailed of the 1870s. The 1600s were were harder to be as precise. But and so we mapped the land cover and bathymetry. Those are in the mapper. You can look at how floods would have behaved on a historical landscape as opposed to the modern landscape. We quantified and I'll speak more about that. We quantified the flood resistance of those different landscapes, and there's a few publications. One is Eric's publication from 2015, and mine was Natural Hazards and Earth System Sciences 2020, the one that I led with Eric and others and Kytt. We worked with the decision makers and natural resource managers to develop, to take in a lot of ideas for nature-based flood risk reduction. But in the end, we developed 3 ideas that had the most efficacy, and I'll briefly speak about those. But they're shown in the mapper also. There was cost-benefit analysis, similar to what Kytt was describing for the Hudson project. And lastly, we created this AdaptMap mapper and also a story map page at the URL adaptmap.info. And so a major goal and what NOAA wanted in this project was to give people more of an understanding of how nature-based solutions work and don't work, and then allow people to interact with the data. And I think there's been, well, I'll come back to that. Allow people to interact with the data. Go ahead, next slide, and learn about sea level rise and adaptation. And I think that was a big innovation of the project also. So here's the landscape. The black line shows the modern coastline, but the colors show the land elevation, the DEM from the 1870s from our reconstruction. So the peninsula grew dramatically longer. The inlet was much narrower, but it was fairly deep, but it was much narrower. Now it's wide and deep because it was basically developed to be a port. Go to the next slide. So all those shallows are, a lot of shallow areas were converted into deep shipping channels. There was a lot of excavation to build JFK Airport, which is sort of the top right, northeast side of the bay, big flat area. A lot of excavation, so there's some deep scour holes. And bottom line is, next slide. Bottom line is that landscape change since the 1870s increased tides dramatically and also increased flood levels in the bay. It actually shrunk the flood zones because, at least for tides, because you no longer have these large fringing wetlands that the water could flow into. So it kind of shrunk the floodable, the area that the tides can move into, and it amplified the tides and it amplified the storm surges. So that's quantified in that 2020 paper, the landscape and habitat changes and the storm tide changes. We showed, which has been showed before for Jamaica Bay in a few other papers of ours and others, that wetland restoration in the center of the bay, which is where they are restoring wetlands, may have a lot of benefits, but it doesn't have the benefit of reducing flooding because you have these deep shipping channels that the water can take to go around those wetlands and just not have to go through them and still get to the neighborhoods with minimal friction and minimal resistance. The nature-based adaptations we did design were actually pretty innovative, pretty novel, and they involve narrowing the inlet to try to mimic the narrower inlet historically, and shallowing those shipping channels and shallowing the bay, just trying to mimic what was there historically. And these so far have been considered by the city, but they would require a massive amounts of sediment, dramatically larger than is used for beach replenishment. So they're not really on the table, but at least we developed some new ideas to add to the mix. Next slide. All right, go ahead, Kytt.
Sure. Yeah, so as I mentioned in the Hudson River tool, we provided a bunch of descriptive statistics. In this tool for Jamaica Bay called AdaptMap, we also completed a cost benefit analysis of the future shoreline based on these 3 different adaptations that Philip had mentioned. So this is just a slide that shows you that we followed the NOAA and FEMA approach for calculating that cost benefit ratio or benefit cost ratio. The damage estimates, again, we used a method similar to the HAZUS MH flood model, but in Jamaica Bay, in this local area, we were able to provide improved data on building footprints and more detailed information on things like the first floor elevation. This image here shows how this area or this building on piers doesn't take on any damage until it reaches that first floor elevation, and then there's an exponential change in the damage function. Again, we included a lot of critical infrastructure in this area in New York City. There's even more data available to make interoperable in a common database. This is just a list of those data sets that are included in the mapper. So the mapper itself, like the Hudson River mapper, it allows you to look at sea levels and storm tides. But in addition, it allows you to look at these different potential adaptations. So, here we have 3 different scenarios for future adaptations. And Eric's team at WCS also did amazing work taking historic information. Jamaica Bay, as Philip mentioned, it's a port, and it has been a port for a long time. So there was a lot of great historic information on the landscape and the bathymetry of the bay, reaching back even to 1609. So the tool allows us to look at 100-year flood, or in this case, 1,000-year flood, how it would look in the present day, and also how that same flood would look on the historic landscape or on a potential future landscape. There's 144 different scenarios in all to choose from. A couple of different sea level rise scenarios that are based on work by the New York City panel on climate change that Philip is deeply involved in. Again, we think that sea level rise on its own is, it's one part of the equation, but looking at storm events on top of sea level rise is really when we get more of an understanding of how people will be impacted. So, both of the tools I've described look at the combination of those 2 things. And then again, the different potential future landscapes or historic landscapes to see how the landscape has changed over time and how it might change in the future. I have to say that, when we were working on this project, we had a bunch of meetings with stakeholders from the community, both, local people and people from New York City and national agencies. And to be able to show how much change there has already been from these historic maps to the present day, it was very useful for getting people to be primed to think about how things might change in the future. So I think that this is one thing that is critical for a general audience, is to see that the landscape that they're in today was very different historically, and therefore it's going to continue to change. So here's an example of a historic base map from 1877. Later on, we can cycle through some of these, and you can just see how the landscape influences the extent and the depth of flooding. Again, it is very important for us to make information available for download. So every one of those over 100 scenarios is is available, the underlying data that fed that scenario is available for folks to use, as well as the statistical and cost benefit analysis based on those scenarios. Again, the time component was something we also wanted to educate everyone about. So each one of those scenarios has a corresponding animation that shows over time how a flood event occurs and then slowly drains back out, as we're seeing here in this example. So some future opportunities we're excited about is to leverage even more cutting edge technologies to, bring home to people what flooding might look like. What's the first thing that, I mentioned very early on, this idea of place and space. When someone opens up a new map, 99% of the time, the first thing that they're going to do is they're going to zoom into their house and see if their house is present. The same holds true for communicating climate risk. So I think that some of these 3D and augmented reality and virtual reality technologies that are just coming of age now are going to be an important thing in the future for folks to understand exactly what 3 inches of sea level rise will look like in their yard or on their house. Philip, did you want to cover this?
A couple of slides. So also looking forward, there's a really strong need for flood and climate adaptation information. Like I mentioned, people don't understand as much about how adaptation will influence their risk and their future damages. And as consequences, most related is that most coastal risk related spending from the federal government occurs after disasters, and very small fraction looking ahead and thinking ahead. Benefit cost ratios for completed coastal flood risk reduction projects average 5 to 1. So much greater benefits of reduced damage than the cost of building. But the areas, we don't have many projects occurring, and we don't have much adaptation occurring. Most areas of our coast still have dramatically rising flood risk. And that's because a lot of people moving and a lot of investment in flood zones, coupled with rising risk due to climate change, particularly sea level rise. Next slide. And so that's one thing that I see, as a vision for flood, or more broadly climate adaptation mappers. People don't have a deep understanding of adaptation. Flood adaptation mappers are gaining wider use. The Corps of Engineers has a story map for one of their ongoing studies right now, the Texas Coastal Spine Study. So they're showing how the flooding would be and how it would be with adaptation or risk reduction efforts in a map format that you can zoom in on and explore. But it's not really free form, and that's the vision that I have here, is that people can gain a deeper, more conceptual understanding by actually even being able to experiment and create their own adaptation choices and options. So that's one goal. We have a proposal out, Kytt and myself and another flood modeler, to try to create a more interactive online adaptation mapper that allows people to draw on their adaptations, and with very rapid flood modeling, still dynamic at a low level, be able to see in real time what the results are, so they can learn about the adaptations and their efficacy. So that's a future vision. Go ahead, Kytt. Next slide. Or actually, now I think we're up to Eric.
Yeah, thanks, Philip. That's actually a great segue into Vision Maker, where you can dynamically interact.
Right. Hi, everybody. Thanks so much for carrying through all the way here. Sorry, we give you a lot of information to think about. So I'll be brief in my comments, and then we can go to the Q&A. So Vision Maker is analogous to some of the things we've already been talking about, but takes a sort of different attitude toward what kind of cultural change do we need to actually truly adapt to a changing climate. Most of the tools that we've showed you to date focus on a set of decision makers who make a decision based on information, and we as the scientific community develop that information so decision makers can get it. But in point of fact, there's maybe another way to think about that, and that's really what Vision Maker is about, which is trying to take this to the level of individuals living in individual communities and ask them, well, what would you like to see? And then giving them some tools so that it's not just a matter of speculation, but they're actually getting some of the scientific information. So I don't know, Kytt, can you advance the slide? Which is to say that Vision Maker is a tool for ecological democracy. So what does that mean? Ecological democracy is an idea that to create the world of the future, the ecology of the future, everyone needs to be involved with it. And everyone needs to have a say on a sort of equivalent kind of basis. So it's sort of a new model. It's, if you like, it's more of a bottom-up way of thinking about how we adapt to the climate and to all kinds of other social factors, as well as a top-down. Can you go to the next slide? So one way to think about that is Vision Maker is a combination of science, of scientific models, of hypothesis testing, coupled with models of sharing that have been developed, say, in social media. So this idea that many people can contribute ideas and that something new and cool and potentially exciting comes out of the process of sharing, and that it emphasizes creativity in a way that this Minecraft brick is supposed to stand in for. This idea of invention. And again, that invention and creativity isn't something that only some people have, but it's actually something that all of us have the capacity to do. And together, if we could create a scientifically defensible, shared vision that creatively moves us into the future, that actually might actually help us adapt to, the really heavy impetus that climate change is putting on our communities, and do so in a way that actually works for more of us or most of us. Next slide. And to do that, we pick up this idea that both Philip and Kytt mentioned, which is that it helps a lot, especially in urban context, to think about the distance past, the more recent past, the today, and then what is the recent and far future going to look like. And cities are so big and they're so heavy in terms of the infrastructure that sometimes it's hard to imagine that very same place was a beach and a forest and a wetland, and it too adapted to the climate and did so for millions of years. And so maybe there's a way to learn something about the past, the nature of the past. At the same time, maybe we could help create better nature in our cities in the future that would make our cities both more adaptable to the climate, as well as better places to live, more healthy, happier, more rewarding places to live. And my work on Mannahatta and Wiliki on the historical ecology of New York City in some way is a sort of a baseline or a template for this kind of thinking. Next. So Vision Maker is a tool, and it allows you to change three really big things. It allows you to change, you can zoom to any neighborhood in the city and you can change the ecosystems of that city, where ecosystems aren't just forest and wetlands, but they include buildings and streets and infrastructure. So ecosystem in the largest sense of a place where living things and the biotic environment and the non-biotic environment or abiotic elements are in interaction with each other. So that's a building, that's my house, that's the road in front of my house, as well as the forest across the way. So you can change the ecosystems of the city, and we have kind of a full repertoire of ecosystems. You can change the lifestyle of the people that live in the city. And by lifestyle, these are sort of modeled average composites, but which are meant to sort of understand the lifestyle component. So sometimes we do things to actually change the infrastructure of the city, but sometimes actually what cities are really good at is changing lifestyles and operating new decision points, new ways of thinking about what it means to live in the city. And then third, we have climate, and climate here is treated a little bit less sophisticatedly than the kinds of things that Philip and Kytt were just showing you. But still, there's this idea of how is the temperature going to change, how is the precipitation going to change, and how is the sea level going to change, and how does that mean in New York City? Next. And then, so the idea is you zoom to your part of the city, and I'll demonstrate this in just a second. You change the ecosystems, the lifestyle, and the climate as you choose, and then the model gives back to you information about the water cycle, carbon cycle, biodiversity, population, and economics. Can you hit that button again, Kytt? So there's a little bit of economic information. Sorry, that's just off the slide. So these are kind of rapidly computed, high-level models of ecosystems of how they process water, carbon, biodiversity, population, and a little bit of the monetary side. And what's important about them is that they're fast, that this is giving you sort of real-time information to make decisions, so that if you're like, well, that's not what I meant to do, then you can change it and do it again, instead of having to engage a supercomputer and it taking months or years to produce a result. Next. And that it does these models, it runs them over the past, over our sense of what the historical ecology of New York City was like on a block by block basis. It compares it to a version of the city today, the modern city, and that it compares your vision of the future so that you can see it in context. And I think this is a sort of theme that runs through all three of these projects, which is trying to think about the contextual information, not just accepting the world that you live in, because of course the world we live in is not adapted to climate change. So like, how do we imagine a world that could be more adaptive to climate change? Well, in that sense, it helps to think of the city as a changing template that changes over time through human decision-making and cultural decisions and so forth. Next slide. And that allows you to share the idea. So, there's a lot of pictures of kids in this because, one of the people we want to engage are young people. But at the same time, we're also hoping that, have seen that, professional people also use this as a sort of way of talking to communities about what they might do. And this idea that it's not gonna be like somebody decides what we do and then everybody just gets in line and does it. That's not how democracies work. Democracies work through this tension of conversation and sharing. And I think it really is helpful to sort of put some of these real problems, and climate change is complicated and hard to know what to do about, into the hands of just everybody. And so that the skeptical, the intrepid, and the creative, and the big tree behind it can all be part of the solution going forward. So I have a little demo here, just some slides. So Vision Maker, maybe I didn't say this, but it's free and it's on the internet. It's something you can go to. The URL is visionmaker.nyc, and this is one version of the landing screen. And you don't have to, but if you make an account, it allows you to save your visions, and you can create a new vision. A vision is the idea of what you want to see in the future. Or you can browse existing visions, and you see those two buttons in the middle, and then there's a lot of detailed help in the Learn More section. Next slide, Kytt. So once you've set yourself up, it brings you to a map of New York City like this. Next slide. We've overlaid that with by combining about 40 different geographic data sets on city infrastructure, natural areas, bathymetry, and so forth. We've created this mapping of ecosystems. These are at 10-meter resolution. Across the whole city, there's 92 different ecosystem types. And like I said, some of these are buildings, some of these are streets, some of these are forests, some of these are wetlands and marine areas, marine ecosystems. Next. And then they are overlaid on top of our reconstruction of the historical ecology of all 5 boroughs in New York City. This is a work in progress, but this is where we were a few years ago. The dark green on this map shows places that were forested, various kinds of forests. The yellow maps show, the yellow areas show wetlands and grasslands. And then you can see the sort of light green teal color is the salt marshes, like those big fringing marshes in Jamaica Bay that Philip alluded to earlier. So you see all this information. Next slide. And you can zoom in. So it's in a web map, so you can zoom in. We're looking at Mill Basin in Brooklyn on the edge of Jamaica Bay. So you can see the modern ecosystems, and there's a tool where you can touch each cell and it'll tell you which ecosystem it is, and all the parameters associated with that. Next slide. You can see that same area, that same part of the city historically. So, Mill Basin it's Mill Basin because it was formerly a wetland that was then filled in, and then people built on it, and there's lovely, canals and things for boats now. But these same conditions that it's, filled salt marsh, filled in this case in the early 20th century, means it's really vulnerable to climate change. And Hurricane Sandy did a real number on this part of the city back in 2012. Next. And then the idea of creating the vision is that you paint your own ecosystem. So there's this palette, if you like, over here on the right. You select the ecosystem you want. It actually has a little paintbrush, a raster paintbrush, and you paint the cells to change the ecosystems. You can paint, solar panels across the, your house or your neighborhood. You can paint bioswales. You can paint, you can paint whatever you want. You can paint a big skyscraper if you wanted. There aren't any constraints because we're trying to emphasize the idea of creativity here, of invention. And then we can have an argument about what's practical or not. But let's just focus on creating new ideas to try and adapt to climate change first. So this is the ecosystem one. All the parameters, again, it's very extensively and well documented parameterization, over 10,000 different parameters describing these ecosystems and the lifestyles and the climate, and all of that information is available through the interface. Next, Kytt. So here you have a vision, say, of Mill Basin, and we've painted something over it. Next. Next, we can also, you could change the lifestyle of the people that live in this part of the city. So one way to use Vision Maker is not to actually change the city at all, but just change the lifestyle of the people living there. And we have these 5 kind of representative lifestyles. You can just keep going, Kytt. So we have an average New Yorker. That's the one on the left. We have an average American. So if everybody who lived in New York City had the lifestyle of the average American, then you would have that lifestyle. We have an average Earthling lifestyle. So if we take a global composite of people all over the world, what would be the lifestyle there? How much food would they eat? How would they transport themselves? So forth and so on. What would be the density? We have a Lenape lifestyle, which is reflecting the Native Americans that used to live in this place and had a very different lifestyle. And then this 5th lifestyle is our eco-conscious lifestyle, as we call it, or eco-hipster. It's the idea that if you take an average New Yorker and then you do all the things that are kind of recommended to decrease your environmental footprint, that's what it would be. So our eco-conscious lifestyle, people ride their bike and they take the subway. They don't drive a car. They call up Con Edison or their power authority and they ask to get renewable energy instead of fossil fuel energy. They don't take airplanes very much. They mostly eat vegetables. They don't eat very much meat, all these kinds of things. And again, the point is that none of us are any one of these lifestyles. They're just composites. But what do we do just by moving our lifestyle around? Vision Maker helps us trying to think about that question. Next. And hit again there, Kytt. Finally, there's a climate selector. So these are based on the New York panel on climate change scenarios, projections from I don't know, 5 or 6 years ago. So there's a climate today. Next, Kytt. There's a historic climate, our sort of version of the 1609 climate based on tree rings, to the best we can understand it. There's a sort of, it was the today climate, was the 2000s one, but now it's 2021, so we need to move that over to the 2021. This was a prediction, and then 2050, 2080, and 2100. And as you choose the climate scenario, it brings up the line. I don't know if you can see the sort of light blue line that's just to the right of the vision. That's the 100-year flood line. Yeah, thank you very much. Yeah, and that changes. It also changes the temperature and the precipitation, which has an effect on the carbon model and on the water model. The carbon model, because it actually is doing a building energy submodel that keeps track of how much cooling you need from, say, air conditioning and how much heating you need. So that then rolls up into different fuel consumption rates. And then precipitation obviously affects flooding based on the precipitation. Next. So, and then you press go and it spins for a minute or two. It actually is pretty quick. If it's just a vision like the size of Mill Basin here, it comes back in about 30 seconds. If you pick a much bigger vision, it'll run, but it may take longer. If you try to do all of Brooklyn, for example, at once, it would take 10 or 15 minutes to come back. But then what you see are these dials that are showing you the scientific data, hopefully in a semi-accessible form. So Kytt, can you go? You press the button. So you got the water model, the carbon cycle, the biodiversity model, the population model, and the economics. Next. And then it's showing you those values for 1609, so the pre-development city, the city today, and then your vision. So in this case, I can't even remember what the exact changes were, but this vision, I think it was adding a lot of bioswales and green streets, that kind of thing, that allowed you to reduce the water cycle. It didn't make much difference on the carbon model. It didn't make much difference in the biodiversity model, and it didn't make any difference on the population model. So this is a vision that's really focused on, changing hydrology. And of course, we all know that there are some people in the city that are really focused on water, and some people are really focused on carbon. Other people, like my organization, are really focused on biodiversity. But the thing is that this is showing you information on all of them at the same time. It's deliberately trying to break down the silos. So you can make a vision that's all about water, but what is the true consequence, or what is the likely consequence for carbon and biodiversity? Well, this is a tool to help understand that, at least at the kind of highest level sort of understanding. Next. And then there's this really detailed summaries. We produce over 200 metrics, and you can drill down, and these are all quantified and in their native units. And you can download this, you can download an Excel file, and you can manipulate it, et cetera, et cetera. This has been very educational, and some educational activities that we've done with school kids, because they can make their own graphs. They can compete to create their own vision, say, for the neighborhood around their schools. Next. And then finally, you can share your vision. This is completely optional. You can work privately for as long as you want. You can also create a group of people that can see each other's visions, but the world can't see it. Or you can make your vision accessible to the whole world. And this is searchable, so you can search by theme, or you can search by parameter, or you can search by geography. Next. So I'm just wrapping up here. So what are the uses? So this idea of ecological democracy. So we're trying to enable everyone to participate in these kind of data-driven, essential, necessary conversations about places where they live. How do you want your neighborhood to change? And for that to be a conversation that we're on a more level playing field. It's not just the experts providing information. It's not just the elected people making decisions. It's actually something we can all contribute to. And we all have to face up to the actually truly enormous challenge of saying, what do we want? What do we want to do with our cities? It's a tool for urban planning. So it gives an opportunity for architects and urban planners to develop these scenarios in very kind of real time. So you can do this in a meeting. You can do this individually. You can do it in a meeting, and the people can work on it at home, and then they can come back and share their visions. We've had a lot of success with middle school and high school kids using this to understand, both the environment and where they live and how New York City has changed, but also understand their role in shaping the future of the city. And I would say that all of these things, in addition to the really fine projects that Kytt and Philip shared before, all just essential parts of an informed climate change strategy for the city. That it just requires such a level of new thinking and new ways of doing business that I just feel so honored to be able to work with these guys to help figure out a way to make a difference. So thank you very much.
Great, Eric, the feeling is obviously mutual. I think that, the work that you do on putting things into context that people can understand, it's really invaluable. I just wanted to summarize like what we've been through a lot. These tools, they provide different levels of interaction. And, when we looked at the Hudson River, it was mostly descriptive scenarios, not focused on the present day. Then when we evolve into Adapt Map, we're looking at a set of future scenarios that were brainstormed by a group of experts in the area, and then you move on to Vision Maker, and as I say, it's an ecological democracy because it opens it up to everyone, including students in primary school. So I think that as you can see, that this realm of research, it's getting more and more interactive, hopefully more and more useful. And, we will have some times for some live demonstrations as well. But before that, it would be great to take some of your questions. So I'm going to stop my share screen and we can do that.
Thanks, Kytt. Thanks to all of you. That was a really impressive body of work, all of these pieces together. And we've gotten a lot of envious questions, wanting to know about how to, how to get these tools available in other places. And I guess I'll start there. I'm going to try. There have been about 25 questions or so. Some of them have been answered, but I'll try to bring together as many as I can. So I'll just, and since going backwards, so since Eric was talking about ecological democracy, which sort of suggests that, through interaction, deliberation, we're going to get change, right? We're going to get democratic change. So there have been a number of questions about whether, the communities that are mapped in some of these tools actually adopted any or changed any of their decisions based on some of the results of this. And I wonder, there was a question about citywide standards in New York City for flooding. And so what has been your experience as you guys have developed these tools? What level of uptake have they had among decision makers throughout the region?
Kytt or Philip, do you want to go first? Or
Sure.
Well, I did answer in the Q&A that, so I'll repeat what I said there. For Adapt Map, some of the adaptations were considered in a subsequent study that had a lot of community interaction. But the general, and certainly we hope that the mapper gets used and gets explored and has had a lot of hits in the 4 years or so since it was completed. But the adaptations themselves were a little bit out of left field and more extreme than people were some of the local people who have the loudest voices, I think, were against them. And I think that that was a big challenge. Basically, it would involve adding massive amounts of sediment, which you might not have a source for. Of course, with harbor dredging, you might eventually get a source for it. In the long run, I feel like they may still be on the table, but so far what's planned for Jamaica Bay is either nothing's going to happen or a lot of shorefront protections that raise shorelines and stop nuisance flooding, or a storm surge barrier is definitely on the table and has more support that would be closed when there's extreme events to protect people. And then the other thing I said was that a lot of work that that I've done with New York City panel on climate change gets used by New York City. It's more where we interact with New York City and they tell us what they want and we give them what they want. And so a lot of their future projections of flood zones and how sea level rise will affect them is through that panel. And so that's one way where we interact more directly with what they want.
Sure. Yeah, just focusing in on the Hudson River tool, we have seen, significant uptake of this tool. There's a couple of cases. We've interacted with the Hudson River Estuary program in Cornell University over a number of years for their climate adaptive design studio. So, in this design studio, they work with local municipalities. In 2016, they worked with Kingston, New York, and they utilized information from our flood models to inform the adaptations that the students recommended to Kingston. We've seen other academic institutions like Hudsonia at Bard College, picking up the data in order to complete natural resources inventories for other grant-funded projects that they're focused on. But I think most importantly, that the New York State Community Risk and Resiliency Act, or Cara, was passed into law a couple of years ago now. I wish I had the year on this, but it was September 18th of some year, a couple of years ago. One of the main things in this was that communities must consider sea level rise, storm surge, and flooding to apply for permits for programs. So, we've interacted with many people who are in this process. For the most part, they've let us know that they've used the tool, and we haven't had to guide them very much. But I think that those are the cases I would point to for the Hudson River tool where we can demonstrate uptake.
Thanks. That's great. I guess building on that, there's been a question about the extent to which the end users, your intended end users, have either had part in sort of designing the portal or have played a role in sort of which decisions could be supported by presenting the data in different ways. So have any of you, I mean, I'm assuming all of you in some way or another have interacted with your intended end users, but I guess there's some interest on the part of our viewers on how that's worked, and whether is that an ongoing process? Do you continuously evolve? Are there resources to continue improving these tools over time, or are they kind of stuck where they are?
Well, I can speak to that from the vision maker's perspective. We had a lot of interaction as we were developing it, and it's developed actually through several iterations. So, so we you know, for example, we convene workshops of a whole variety of different end users, government and non-government, and in the education sphere who's advised us, and then we would give them feedback, and then we would design according to that. And we've also had a whole group of schools. We've had 40 schools, middle school and high schools, across all 5 boroughs in New York City that have worked on us to help develop Vision Maker. So that's all good. But actually, one of the places it's fallen down a little bit is it's all been grant funded. We were, fortunate to get some seed funding from the Rockefeller Foundation, and then New York Community Trust, and then NOAA, and then the National Park Service. We're all familiar with this, right? But Vision Maker needs a new retool. These tools, they go out of date so quickly, actually, that it's really hard as a nonprofit to keep up the level of fundraising and maintenance that's required to maintain these things. It's actually made me appreciate books a lot more. Like you do a book, it's a lot of work, and you get it, it's all done, and then there's an institution like the library to take care of it. But we don't have that for like an interactive web mapper like Vision Maker or like the other ones you've seen. That doesn't exist. So it's a huge question going forward about how do we, not only how do we develop these, but how do we maintain them and turn them into the next, version 3, 4, 5, 10, because I think they're essential to the way we make progress in the future.
And a follow-up on that would be, not just updating these existing tools, but if you wanted to expand to other areas, I wonder if any of you could talk about sort of the level of effort, for example, the Delaware River Estuary to develop something like this, or Philadelphia, does it require, how scalable are these tools? How easy is it to sort of swap in other data and use the same tool in a different place?
Yeah, well, I'll be brief, and then I'd be interested in what Kytt and Philip have to say. We designed Vision Maker to make it portable to different places, and then we've had 3 huge proposals to try and do that, to adapt it to new situations, new contexts, and none of them have come through. So, which maybe is just par for the course, but I think it's it's sometimes hard, to find the right connections and the right relationships, and then the right funder is willing to take a chance.
Sure. Yeah, I could add on to that. I think I agree with what Eric has been saying. One thing that we found, at Season, where we produce many of these tools for other contexts as well, is that the tool uptake is certainly correlated with outreach. So, when you're doing a lot of outreach, the tool is usually being used a lot, and it organically it spreads at those times, and then it drops off when you're not doing the outreach. We've had the golden eggs here with AdaptMap and the Hudson River Mapper, that these tools have been around for a number of years now, and they're still generating a lot of excitement and getting a lot of usage. That's more the exception than the rule. But I do think there are opportunities out there to do exactly what you described, Franco, which is to create generalizable systems that can be applied to different contexts. And more, the proposals that we're putting out these days are focused on doing that, rather than looking at case studies in a single area. However, I think, though, that there's a lot of learning that we do through the process as well. And, getting dirty in a place like Jamaica Bay, where there's a lot of information, and then trying to take what we've learned there and go to some place like, India, where data availability is very sparse. It's invaluable to understand that spectrum. But I do think that there is a lot of effort involved, and that, more and more we're trying to create modular tools in order to reduce that effort for places that are less data rich.
And I mean, sort of an interesting connection to that answer is also this thread going on in the Q&A about citizen science. And I wonder, Eric, you're talking about how difficult it is to update your model, but yet people are inhabiting these places that you've modeled or that you've simulated. And if there were an opportunity for people to, in a crowdsourcing kind of way, input information, I wonder how feasible it is to kind of automate some of the updating, at least through citizen science.
Yeah, that's a good idea. That's a good idea. I mean, one of the ironies of my work is, in some ways, the 1609 layer hasn't changed very much, right, over the last couple of years. I mean, I'm continuing to adapt it, but the city itself changes all the time, right? So we had the initial impulse of work in sort of the 2014 and 2016, and I think we got something that was pretty much correct, but the city continues to change, and new buildings get built and other ones get taken down, and streets get opened and streets get closed, and that kind of really detailed thing is hard to keep track of. And so I think some combination of New York City's fortunate because now they put out the Map Pluto, the land use data set, on a regular basis. So to automatically ingest that instead of doing it by hand, and then at the same time, then to have a system to flag changes from the community would be wonderful. But even more important is creating the visions, right? I mean, I have to say that the thing that's been most challenging about Vision Maker is that when you actually go to communities, and we've done a lot of this work, particularly in the Jamaica Bay, and you say, what would you like to change? It creates this really interesting but really difficult conversation about all the constraints people feel, which are political, social, economic, all the things we talk about all the time, but they just stand in the way of us making real changes to climate change. And then you look at like Philip stuff, and it makes you really worried for society. Like, how do we square that circle between understanding that big changes are required and yet, feeling like we're so locked down by the systems we've created for ourselves?
Absolutely. It's really interesting to, on the one hand, the spectrum of tools that have been presented, on the one hand, really detailed modeling of one place, and on the other hand, a lot of information about a very big place, and both yet, contribute to a public discussion about the possibilities of the future, that it wouldn't happen if the tool didn't exist. I mean, one is really focused on a couple of options, but really quantifying the differences. And the other is looking like, look at all these metrics, pick your metric. Which one do you care about? And those are both parts of, I'm assuming what you're calling this ecological democracy, is being able to talk about a lot of things, but also talk in detail. Well, this is great. I don't know how much time you guys wanted for demos. I'm trying to keep up with all of the Q&A while talking to you. I feel like a lot of the questions, there have been some very specific questions about, have you used this in coastal, or have any of these tools been used for beach restoration or environmental conservation, horseshoe crabs, migrating species? I don't know if any of you want to get into any of these very specific questions, or if we should move to the demos, and then the folks who are not demoing maybe answer some of those more specific questions in the Q&A. How does that sound?
Sounds good.
Sure. That sounds
can
good.
go either way. It's up to those two if they want to do demos, but I could do either.
Well, I think especially for the ones Kytt has to show, they're so like the presentation of them is so much, but actually the implementation of them is pretty cool, and it makes it seem easier than it might have looked otherwise. Not to
so let's do it. Yeah, let's do it.
Yeah, sure. It's just a a couple of things that I wanted to show off. So, what we're looking at here is the Hudson River Flood Impacts Decision Support System. And, as Erica just said, the implementation simplifies things a whole lot. So, it's a wizard-driven system here where we're choosing a community that we're interested in. So I'm going to choose Westchester County. I'm going to go ahead and choose Peekskill. I'll choose a sea level rise scenario, keep it modest at 6 inches, and a return period of a 100-year storm, which we know is a lot more common than every 100 years. So when I submit this filter, the map takes me to the community of interest, and it shows me these impact summaries across those 3 different themes that I mentioned. So it shows me the critical infrastructure that might be impacted by the scenario. So I know that there are 3 bridges, for instance, that might be impacted. So if I look at my transportation infrastructure and I turn on the bridges layer, I can see that those ones that have a red fill are the ones that intersect with the flood zone for this scenario. And then the bridges with a white fill are the ones that do not intersect with the scenario. Then if I want to get more information, I can click on the individual components. In this case, the bridges data tells us something about the material it was built with, and that one was built out of steel. We also have the natural resilience features, the total inundated land area, as well as the amount that's impervious. So if I look at the ecology tab here, and I want to look at the tidal wetlands that are in the area, if I turn this on, you can see up here that Peekskill, it does intersect with some Hudson River tidal wetlands. So, even though this area is showing up as flooded in our model, it may be that these natural features could reduce that flooding. So, that's where in Adapt map, we're modeling the landscape, but in this Hudson River mapper, remember, we're looking just at a bathtub model. But at least now the decision maker can look and understand where these areas of overlap are. Also, in terms of social vulnerability, switch on the social vulnerability index layer. I'm going to zoom back out. What we'll see is that a lot of Peekskill, and especially the densest areas in Peekskill, are also considered high vulnerability areas. So this can tell us where to siphon resources, as we all know the resources are always limited, unfortunately. Then the last thing I wanted to show was the ability to upload your own GIS data. So before the call today, I downloaded a file from Westchester County GIS. And what it is it's the location of sewer plants. So sometimes we acknowledge that municipalities may have local data that is more accurate than what we could provide in the mapper. So you can upload that. So if I take this wastewater facilities and I upload it, what it does for me is it converts it into a GeoJSON file. If I save that file, just call it sewage plants. I can take it and drag it and drop it onto the map. Now for Westchester, we see these yellow spots that have shown up are the location of these local sewer plants. So this is one way to make a mapper more modular. so that you can upload newer, better information. So there's a lot more we could do here, but in the interest of time, I switch over to Adapt Map, and so here's the airport. So again, we're looking at a 100-year flood right now in the present day landscape, but perhaps we wanted to see what this same 100-year flood would have looked like historically. So if I move this slider to 1877, a couple of things happen. One is I see this digitized base map of the 1877 landscape. You see these numbers on the base map are bathymetry measurements that we used in order to create the flood surfaces. And you can also see that the extent and the depth of the flooding has changed quite a bit. So if I switch back to the present day, in the present day, we have a lesser extent of flooding than we did historically, but where it does flood, it floods much deeper. So using that information, we came up with the future scenarios that Philip described. This help page just describes them in more detail. I won't go into it now. But if we go back and we look at this same flood scenario, and now we want to say, what does it look like under some future adaptation? So if I look into scenario 3, where there's been narrowing of the bay and a shallows restoration, we see that in this scenario that reduces the depth and the extent of flooding. So, it allows folks to look at the spectrum from historic to potential future risk and try to put that in context. So there's a lot of other components here that we mentioned in the slides that, are interactive, but again, in the interest of time, I'll stop there.
Can I just ask a question going back to something Phil was talking about, the difference between the bathtub models and the dynamic models? And I'm wondering with Adapt Map, if you kind of pre-run the models and then really what's happening on the portal or on the web interface is people are selecting between previously run models. You're obviously not running the model in real time. Does that give you the opportunity to do dynamic, do the more sophisticated dynamic modeling, save the results, and then have the public able to access the dynamic modeling results through this portal? Or are you kind of obliged in some way to, because of the way you're visualizing it, to do the bathtub modeling?
Well, there's no bathtub modeling for Adapt Map page. It was all dynamic flood model up into neighborhoods. But there's no free form ability for people to contribute something new, right? That's the shortcoming we'd like to address with future mappers. But yeah, right now there's no ability for somebody to innovate something new. And the reason for that is because that model require, I was using 100, 80 extratropical cyclones and 64 tropical cyclones for every landscape and sea level rise combination. So, which is something like 16 combinations. So thousands of simulations, so it took a supercomputer and a lot of pre-computing. So that's probably not the way to do it if we want to make this be more common and be more widespread. So we're trying to figure out ways where, and also it's not as interactive as if we could come up with a really rapid flood model. So that's our wish going forward.
I wonder if any of you have anything to say. I mean, we do have a significant number of students who participate. The skills that, the sort of technology behind the scenes here, there was a question about what coding, what these types of tools are coded in. But, to what extent, I don't know if you can generally parse it out this way, but to what extent is this really coding versus, data analytics versus hydrology, hydraulics, oceanography, basic science? Just for the students who are kind of attending, do you have any thoughts on all three tools?
I can speak from the vision maker perspective. So our team that initially created it had an architect / urban planner person, had a designer, like a visual, web designer kind of person, a couple of programming experts, and then scientists, because it took all of those skills to work, and then lots of coordination to make them all work in concert with each other. So I think there's lots of opportunities for different people. And then we've worked with a lot of educators and social scientists, in the sort of subsequent phases of vision makers. We've expanded out, and geographers and historians on the historical part, including some archaeologists for the Lenape components and so forth. So.
Sure. Yeah, it does take a village definitely to make one of these, and I think having Philip's scientific expertise in the flood modeling obviously it wouldn't be here without that. And then where our team at Season picked up from take the baton from Eric and Philip doing the great science work is to then measure human impacts. There's a lot of coding involved in the data production, using things like Python and R. If you have the opportunity to take some spatial analysis courses, it would be a good thing. And then there's the whole front end of it as well, which is, for us is mostly JavaScript. But there are web designers that are involved that, are experts in creating user interfaces that are we think are user friendly. Then there's a lot of testing with, beta testing with actual users so they can let us know that it wasn't actually user friendly, and we go back to the drawing board. So these things are very much an iterative process, and it takes years to get to a production level product.
Thanks. So I will, we only have about 10 minutes left. We don't have to use all that time. I did want to ask one sort of question myself, which was just tying into our previous two sessions were about environmental justice. And I know that there is this specifically with flooding, this sort of perverse situation that happens where you have neighborhoods where the real estate value of the buildings may not warrant, according to conventional benefit cost analysis, the investment in protection. It's a big problem, right? So that you'll have exactly where you have the most vulnerable, you don't have the economic case for protection. And I'm wondering, to what extent these tools, in the Hudson River tool, you did show sort of critical assets and stuff, but is there a potential for, a more environmental justice focus to some of these, or are you already thinking about that, how to bring in that sort of vulnerable, so that the benefit cost analyses will justify protecting certain places, we know that, but there's other people that need to be protected, and can these tools help them to kind of make that case?
I could say briefly that there is a movement toward not just quantifying damage reduction, for sure, and that's a key issue. We're modeling mortality from flooding actually around Jamaica Bay, in that same domain on same models for AdaptMap. The Corps of Engineers, I just heard a story where I think it's something that's not happening much yet, and I don't think it's policy, but there's a project on the Mississippi where the benefit cost ratio was well below 1, but because of life safety and people being in danger, it got elevated to be built. So there's different ledgers, right? That's one way I think they refer to it. And one might be ecosystem services, of other, or it could be ecological quality, I think is what the Corps calls it. There's social benefit, and there's economic benefit. So, and under social benefit might be the life safety and danger. So I think that's a good direction to go. Obviously, I think that definitely is a good direction to go. It can't just be driven by money only, for many reasons.
Yeah, our attitude is give people information and let them do what they will with it, So I'm trying to deliver the tools in an accessible way that, or at least it's, you have to have use VisionMaker, you have to have an internet connection. So there's some basic level of justice issues there maybe, but I think the more you make it possible for people to make their own arguments, then the more likely it is that people can speak for themselves and speak up and be heard to make a difference. But I have to say that there's also this historical legacy fact that so many of the like in New York City, we filled in so much of our salt marshes and then built, housing on it that's now occupied by, lower income people that have been, historically marginalized in all kinds of ways. So there's that kind of environmental justice issue that, again, climate change is really going to sharpen that issue because those, some of those communities will be the first ones to flood. And the solution can't just be, make them all, fancy places, gentrified places, right? It reminds me a little bit of, I don't know if you remember, after Hurricane Sandy in Manhattan, it flooded, South Seaport flooded a lot. And the Bloomberg administration response was, well, let's build it bigger and put luxury housing on top of it. Let's build Battery Park City on the east side of Manhattan, right? And I think that's exactly the wrong way to go. That's exactly the wrong way to go.
Yeah. Okay, well, I have to thank all three of you. This has been a really spectacular session. We've got a lot of good debate back and forth. And just remind our viewers that there were a lot of questions like, can we get this presentation? I want to show it to these people or those people. All of our CC Run presentations are webcast and they will be archived on the CC Run website. So give us 2 or 3 days and we'll have it posted. And feel free to share the link with whoever you'd like. And also please come back and join us next month. I believe we're continuing this this theme of tools. So the first Wednesday of every month is our session, and we'll be back in April. So looking forward to seeing you all then. And thanks again to Kytt, Philip, and Eric for spending the afternoon with us.
Great. Bye, everyone. Thank you so much.
Thanks.